Welcome back. Good to see you again. This is part 3 and the final part in Trig Identities and the final part in the presentations on trigonometry in this particular course. Have a look around the screen. Wow, have we really looked at all of these? I think so. This one. Oh yes, lots of stuff here. Do you remember? Because Huddyism is, maths learning is sequential and cumulative, and you've got to accumulate this knowledge and skills so we can build up. But the burning question now, as we go into this last presentation, is do you think the sine of twice an angle, here it is, would be just double the sine of the single angle? Do you reckon that'd work? All right, I hope you have an answer. Think about it for a minute now. You might like to pause the presentation. And here's the answer. No, it wouldn't, would it? Because let's say you wanted the sine of, something like pi on 3, which is 2 times pi on 6. Well, here the sine of pi on 6 would be a half. Double it would be 1. Hey, no. Those two aren't equal. The sine of pi on 3 is not 1. It's not just 2 times a half. And then if you've got something like 60 degrees in here, or pi on 3, then the sine of pi on 3 is root 3 on 2. Double it, you get root 3, and that's outside the unit circle. So it's not going to work, is it? It's going to be more complicated than that. And we saw down here, if you were in the last presentation, the result for tan, right down the bottom right-hand corner here. Tan 2a is 2 tan a of 1 take tan squared. And there is a fairly simple relationship between sine of a double angle and the sine of the single angle. Let's go and have a look and see if we can find it. Okay, so let's see if you can derive it for yourself. Here it is here. I'm going to challenge you here to try to derive this relationship. The sine of a double angle is 2 times sine of the angle, cos of the angle. How did that come about? I'm going to give you a hint. I'm going to ask you to look at sine of 2a as the sine of a plus a. Now we've done that before, haven't we? The addition formulae. Sine of a plus b. Sine cos plus cos sine. Remember that from the last presentation. I want you to pause this presentation now and see if you can show that the sine of the double angle is 2 times sine of the single angle cos of that single angle. All right, we're back now. Let's do it. Sine of a plus a is sine a cos a plus cos a sine a, using the addition formulae. Addition formula there. Okay, so this is one lot of sine a cos a, and cos a sine a is the same. Multiplication is commutative, remember. It doesn't matter which way around these two go. Multiplication is independent of the order in which you multiply things. It's commutative. Have you seen that word before? I hope you have. Commutative. Multiplication is commutative. So here we've got 2 lots of sine a cos a, and we have done it. Are you feeling powerful? You can actually understand that, and you're not far away from being able to do it yourself and discover new stuff. This is really exciting. All right, now the next challenge is if you can actually change that then to cos 2a. How would you do cos 2a? Could you do it in a similar way? What would we say? That's the cos of a plus a. Is that right? Okay. What I want you to do is to pause the presentation and have a go. You'll need the addition formula for cos of a plus b now. All right, let's see it in action. Cos of a plus b is the pattern cos cos and minus sine sine. Remember that? The addition formula in Cosland has the opposite sign between the two products as what it is in the middle here. So if it's a plus, it's a minus in the cos cos sine sine pattern. Let's have a look at it. I think we've done it already. Cos squared A takes sine squared A. So that's an as required, isn't it? That's the first line up there on the left, up here. Come up here. All right. Now, can you manipulate that, maybe simplify it in some way to get these other two forms, which could be useful if you want to just work in a cos expression or a sine expression? Okay, pause the presentation, think about what we've done, and can you simplify this into just a cos expression or a sine expression? Let's have a look at it now. Sorry about that one. Let's have a look at it now. So, since sine squared A plus cos squared A equals 1, that's the unity identity, isn't it? We established before. We can say that, what will we do first? Let's do the cos one. So sine squared A is 1 take cos squared A. Therefore, cos 2A will equal cos squared A take sine squared A, which will be 1 take, we're replacing sine squared, so let's just rub that out here. So here we go. It'll be cos squared A take 1 take cos squared A, which is cos squared A take 1 plus cos squared A, which is 2 cos squared A take 1, as required. Okay, and over here you could put it differently. Here, cos 2A replacing cos squared with 1 take sine squared. Okay, can you see that there? And so here it is 1 take 2 sine squared A. All right, as required. So these are helpful ways of using the unity formula here and getting an expression for cos 2A with just sine squared in it or just cos squared. So you might have cos 2A in an expression where there are sine squared A or sine A terms. So you might choose to use this replacement for cos 2A, getting an expression overall in just sine. Okay. Tricky, isn't it? But it's fun. It's rather like an interesting puzzle there. So let's go down and see what we can do now. Okay, so these screen clippings are from Hayes and Harris publications. And let's have a look. We're given a sine of an angle and the cosine of the angle. Find the sine of the double angle. So these are called double angle or duplication formulae. Double angle for obvious reasons, or your duplicating angle, duplication formulas or formulae, whichever way you want to put it. Okay, so let's have a look. Sine 2A. First of all, we say it's 2 sine A cos A. And then we can put the values in from up here. And we can easily find it. Okay, what about cos 2A? We can use 3 different ones. Let's just use cos squared take sine squared. So it's this one squared minus this one squared. There we have it. And it's all over 25, so 7 over 25. So you can actually check, like this dude's saying here, using the calculator and see that it works out. But what we really want to do is use algebra with trigonometry and do it mathematically. Okay, let's go down now and have a look at some examples for you. I want you to have a go at these. We'll hide the answers just for a minute. Okay, so pause the presentation, have a go. I'm going to show you the answers in a minute now. So coming down here, let's have a look. There are the answers. Okay, did you get them? If not, go back, check the example, see what we're doing, and have a go. All right, let's move on. Here we have another example. Things that we can do to help us work with sine and cos and sine of 2 alpha and cos 2 alpha and so on. So here we're given the sine of an angle and we're told, oh, what's this mean? Pi and 2 is less than alpha is less than pi. Let's track that out. Let's find pi and 2. Start with, yep. Okay, so round to this position, pi and 2, top of the axis. I don't think we really need to circle that. That's not really where the angle is. Okay, so it's escaping me here. I just want to rub this out. Okay. All right, so it's come down a bit now. So this is the angle here, pi on 2, and less than pi. So the angle pi is on this line. So we're working in the second quadrant. Find the value of sine 2 alpha without using a calculator. Okay, so it's quadrant 2, and cos is negative there. It's the x-coordinate, isn't it? The x-coordinate is negative in that quadrant up there. So what are we going to do? We need to find cos alpha. No, we need to find sine 2 alpha. So what can we do? We know that sine 2 alpha, down the bottom here, I would have put that first perhaps, sine 2 alpha is 2 sine alpha cos alpha. That tells us therefore, although we've got the sine, we also need the cos. So here we are, done this before, cos squared plus sine squared is 1. So put in the sine squared, take it away. Find the root of it, don't forget it's plus or minus. You choose the negative because it's in the second quadrant as stated up above, and therefore the sine of 2 alpha is 2 sine alpha cos alpha, substituting them both in there. So just looking at the picture over here, that alpha is in that second quadrant. Okay, some for you to try. Let's have a go, just building up slowly here. So question 4, I'll hide the answers down there. So question 4, try to do the same thing. Pay attention to which quadrant you're in, because that affects whether sine or cos are positive or negative, doesn't it? So adjust that as we did in those examples. All right, pause it, have a go. Here we go, let's have a look at the answers. Okay, mark your work there, check it out. Remember, we're doing it accurately, so we're leaving it in surd form, those irrational numbers, non-terminating, non-recurring decimals. Okay, so there's only one accurate way of representing those. We can't do an infinite number of places. Therefore, you're going to have to leave it as root 5. So these are what we call the exact form for the answers. Okay, that's one of the values of doing it by mathematics and algebra here rather than going to the calculator. Let's go on. What else can we do with this? Here's something else. Just little tricky do's, different little rearrangements, keep you on your toes with the algebra of trig functions. So now we're given the cos of 2 alpha is 3/4. Find the value of cos alpha and sine alpha. So if we've got 2 alpha, we need to choose a formula. We could choose this one. You could have used 1 take 2 sine squared and gotten sine alpha first, but they've chosen here to use 2 cos squared alpha take 1. Remember, there's a choice of 3 for cos 2 alpha. We just proved them up above. So cos 2 alpha is 3/4, so 3/4 equals 2 cos squared alpha take 1, and therefore adding 1 to both sides, cos squared alpha, or 2 cos squared alpha equals 7/4, dividing by 2, cos squared alpha equals 7/8. So now you have to find the square root of that. Don't forget, it's a squared equation. There's a positive and negative solution here. 2 solutions for that squared equation there. And root 7 over root of 8, just check you can do this, root of 8 is the root of 4 times 2, root 4 by root 2 is 2 root 2, simplest third form, that irrational number there. Okay, so now it says up the top here, come up the top, alpha's a cube. So therefore it's in the first quadrant, so cos alpha is this positive one only. Okay, and we've just done it. Now we've got to find sine alpha. Now we could find sine alpha by using cos squared plus sine squared equals 1, as we did before, or you could go back and do it with the same formula. Okay, and so on. Okay, just remember here that there are 3 forms for cos 2 alpha. So here, what they've got here is just what I said. Sine squared plus cos squared is 1 could also be used here. Should we check that? Okay, so if we did it over here, cos squared alpha plus sine squared alpha equals 1, take the cos alpha from here, so it's root 7 over 2 root 2 squared plus sine squared equals 1. So this is 7/8, we said that before. And now subtracting it from both sides, we should put implies here, the implication sign. So sine squared alpha is 1 take 7/8, which is an eighth. So sine is plus or minus 1 over root 8. But here it's in the first quadrant, so it's only the positive answer, 1 on root 8, which is 1 on root 2. So it's another way of doing it, isn't it? When you've got a cos and you want the sine, you can always go to this unity because it equals 1. All right, your turn. Let's do some and get your schools up here. So here's an angle, and we're told, here's a cos of a double angle, sorry. We're trying to find the cos of the angle, and they've got some answers straight there, so you can actually check it as you go. Right, pause it and have a go. I'm going to go on. Some more excitement awaits us down below here. Some more rearrangements and stuff. Now this is interesting. Use a double angle formula to simplify this. Hey, that doesn't look the same format as a double angle formula. Double angle formula is cos squared take sine squared, or 2 cos squared take 1, or 1 take 2 sine squared, or 2 sine alpha cos alpha. We've got a 3 in here. Well, we could put in a 2, couldn't we? And then multiply it by 3 over 2. That's a nice little tricky do. Remember that one? So that is 3 over 2 lots of sine 2 theta. What about this one? Let's factorise it first of all, because then we see, it is actually the format of a double angle formula. Remember, cos squared take sine squared, or 2 cos squared take 1, or 1 take 2 sine squared. They were sort of the formats. And here, of course, it's 2 cos squared 2b take 1. So it's actually the double of 2b. Are you flexible? The idea here is if you have cos 2a, it's 2 cos squared a take 1. But if you made that 2a, this would be the cos of 4a. So it's a double angle formula. It's any angle here and it's duplicate or double over there. So if we've got 2b in here, it's actually a 4b for the double angle. Okay, don't get confused now. This is the generic nature of those formulae. In a minute, I'll discuss that with you. All right, so pause the presentation, have a go at a few of these, maybe every other part, the alternate parts. Okay, I'll bring up question 7. I'll bring up 7, we can do all of them, 7 and 8 here. Okay, so pause it, have a go, and we'll have a look at the answers. Let's come down here now. Here are the answers. All right, how are you going? Getting a headache? There's a lot to think about here, but what you're doing is being very flexible in working with trig expressions. So if in a problem we get a complicated expression, we can hit it with various of these identities and simplify it down to understand it better. All right, come on down now and have a look here. I'm going to ask you to look at a new format for a trig expression. Why might you want to express y equals sine x plus cos x as this? I take it the two are equal. Do you want to check that out? Yeah, I think we should. Wasn't going to, but I think we should. I want you to check out, so pause the presentation and use the addition formulae to check out that this does give sine x plus cos x. And then I'm going to do it. So pause it. All right, here you go. Let's do it. This is root 2 sine x will be root 2, and let's do the expansion here. Sine cos plus cos sine. Remember that pattern? Okay, this is the addition formula. So this is root 2, sine x cos of pi and 4 is root 2 on 2, cos x, and then sine of pi and 4 here is also root 2 on 2. Multiplying by root 2, you get root 2 by root, we'll just make it simpler here, I'm running out of room. So here what we could say is root 2 by root 2 is 2, over 2 is 1. That's 1 sine x. Plus, multiplying this through here, that's times, root 2 times root 2 is 2 over 2, again it's 1. So it's just 1 cos x. and it's as required. We have shown that this thing is the same as sine x plus cos x. And that's what we're going to do in this section of the presentation. Change the sum function to an auxiliary angle form. That is, the equivalent sine of x plus some angle. And that's called the auxiliary angle. But hang on, let's go back to the original question. Why might you want to do that? Why would you like to give this lots of ticks, whereas you give this a bit of a question mark? Can you see it? Well, without a calculator, we can actually roughly draw and understand this form of the function, can't we? Sine x plus cos x would be hard to get our head around. What would be its maximum and its minimum? Where would they occur? Okay, now, if this is the equivalent form, we can say sine is has a maximum of 1 and a minimum of -1. Therefore, put a root 2 in front. This function has a maximum of root 2 and a minimum of neg root 2. And it's also a neg pi on 4 translation of sine x. So we can see that the maximum is going to occur at pi on 2 take pi on 4 or pi on 4. Wow! That's all because we were able to change this into this form. Let's go and do it and see the power of this auxiliary angle form. Okay, so here it is. If you've got that form, it's very hard to talk about its maximum and minimum and where they occur. So we would like to change it to one of these two forms. We usually go with sine because we think of cos as a what? A neg pi on 2 shift of sine, if you like. Okay, this is called the auxiliary angle formula because you're using this angle rather than just x to help you. Auxiliary, assistance, aid from the Latin. So this is to aid you in understanding the function. All right, so let's go down and see how do you do it. Good question, Huddy. Okay, and here's more screen clippings from Hayes and Harris publications. So here we are, let's do it. So we want that in this form where k is a positive and alpha is some angle on the first revolution. We want the angle to be as small as possible. So if that's going to be equal to that, then expanding this side, sine cos plus cos sine, that's the addition formulae, and then we get this. We're going to package up the sine term, so that's, how many of those we've got? K cos alpha is the coefficient of sine, then let's put the cos term on the end, and k sine alpha will be the coefficient of that. So now what we're going to do, I don't like comparing coefficients, equating coefficients. So here, how many sine x's have we got? We have 3. So therefore 3 must equal the number of sine x's we've got over there, equating coefficients of terms. Cos x, we have 4. Over here, therefore, that must come to 4. Equating coefficients. So therefore, the cos of alpha is 3 on k, the sine of alpha is 4 on k. And we know that sine squared plus cos squared is 1. Hey, we can come down and hunt down k. And we're going to leave it as a positive here. Okay, we could use it as a negative. That gets messy out the front, don't we? We don't want a k up the top here, out the front, which is negative. That's going to confuse it a bit. It'll still be correct, but we choose to have a positive there. Now we need to find the angle. So go back up here. The cos of the angle is 3/5. The sine is 4/5. So we'll go cos neg 1, and there's the angle in radians. Make sure your calculator is set up when you're using this cos neg 1 in radians. So with the Casio, that's shift menu button, because that's set up, sitting on the top of the menu button. And when you do that, you get a window and you go down to angle and you choose radians here. Okay. Why radians? You might say, why can't I use degrees, Huddy? Well, have a look at it back up here. The domain of alpha was given from 0 to 2 pi. 2 pi means you're measuring angle alpha in radians. So therefore, there's our answer. And wow, what can we say? What is the maximum value of this function? It's 5, because it's 5 times sine. And the maximum value of a sine function is 1. What's its minimum? Neg 5. How does it compare to sine? What is the translation? Oh, it's been translated neg 0.927. We've got an immediate insight into this sum function. This is powerful and interesting, isn't it? To really get up close and personal with that function and understand it. All right, I want you to do some now. So you might have to study that process there, and here we come down to some of the problems from Hayes and Harris. So I want you to have a go at a couple of these from each of the questions, okay, and see what you think. The first two are in sine land, and then these you can use cos. Same process though. And for a bit of a challenge, so pause presentation, have a go. I'll bring it down to 5 now. 5 is a little problem, so you might have a go at that as a bit of a challenge. And Hayes, they colour this blue, meaning it's more challenging. Okay, pause it, have a go. I'm going to show you the answers now. So come down and have a look. And there we have the set of answers. So go back, check your work, make sure you're happy there, and let's go on. Let's have a look at the last little bit now here, and these are very powerful. Now, we don't use these as much as what we have in the others, what we would with the others, but sums to products and products to sums are useful in doing some work in calculus later on. So, well, you just have to stick with me there because I can't actually show you that until we've actually done some calculus. Let's go on and have a look at what these formulas do. And the way Hayes have presented this is to say to you, we can change this sum into a product. Okay, and that's what we're doing. Sum of two angles, first angle and second angle, and we can change it to a product. How would you do it? Well, you'll blow this apart over here with two applications of the addition formula. And amazingly, it comes to that. And what you can notice is that the product is, well, 2 times the product is half the sine of the sum plus half the sine of the difference. So if you've got a product sine A cos B, when we've established this, you can say that as a sum is half the sine of the sum of the two angles plus half the sine of the difference. Okay, so I want you to actually use that idea, the generic idea here, sine cos as a product is half the sine of the sum of the two angles plus half the sine of the difference, no matter what those angles in there are. See what I'm trying to give you? A word or generic approach to them. Then what's this one down here? You can show this. So a product of cos can be changed to a sum half of cos of the sum of the angles plus half the cos of the difference. So these are actually subsidiaries to the addition formula, really. They're very handy in calculus later on. And then what about the difference formula? So these are expressing a product as a sum of coses. What about this one here, difference of coses? What do you got? Well, here's the result. If you had sine, then changing that to a sum or difference, it's half the cos of the difference of the two angles minus half the cos of the sum. Getting a bit intricate here. See, they're putting in different order here. Okay, so that we can change products to differences or sums of trig functions. Okay. All right, so down here is a bit of a summary. Sine cos, cos, and sine. Excuse me. Okay, these are called products to sums formulae and very useful in calculus. So we're having a little introduction here. All right, now, can you go backwards And the idea here is that we're going to do some exercises up here to say if you have sine plus sine, then it's 2 sine of half the sum, cos of half the difference. So you can play with these expressions if you like, but the idea now is to come down and to end up with this idea. Sine plus sine, the sum of 2 trig functions, can we change it to a product? So here it is, sine plus sine is 2 times sine half the sum, cos half the difference. That's how you would apply it. And then sine minus sine. Sine minus sine is 2 times cos half the sum, sine half the difference. So they are fairly complicated, aren't they? And if you just finish off here as an introduction to these, you do more of these later on in maths, you can also do cos plus cos, cos minus cos. So I want you to think of these, cos plus cos. You should have an angle in there. This is just the way you think about it. We shouldn't write this without an angle. It's 2 cos half sum, cos half difference. Okay, and cos minus cos. Look out, it's neg 2 sine a half sum, sine a half difference. This is the way I want you to think about it. In other words, the angles here, where do they occur here? Half the sum and half the difference. Okay. So have a go at those and see if you can see how they're derived. But now I want you to use them to convert these to products. Okay, so go back and try and change those to products. All right, let's just get rid of that. Let's go down and have a look at the answers now. And there we have it. Almost. I'll just go back here a bit. Question 1, 2, and so on through there to question 6. Okay, so have a go and see what you think. That's a bit challenging. If you're going on with maths, then that's going to be of some importance later on in calculus. All right, we'll study that carefully. There's a lot there, and particularly the sums and products at the end. You might have to ponder over that, talk to your classmates and your teacher. All right, well, that's the end of this series of presentations on basic trigonometry at about year 11 level. And what we'll do now in this course is move on to other topics. So I hope to catch you then. Cheers for now.